So thank you for coming to this lunchtime talk. I'm Ben from IMC. I've got half an hour with you now, so I'm going to try and fit in time for questions at the end. But if you have any, I'd ask you to hold them until the end. Thank you. So my topic today, it's how to simulate a low latency exchange. And hopefully by the end of this, you'll have a high level idea of how you could do this in a HFT environment. So how am I going to do this with you? Quite straightforwardly, I need to first set the landscape. I need to tell you a story. I need to make sure you understand how this simulation is going to work, and to do that, you need to understand the environment in which it's operating. Then I need to answer the question of why. Why would you want to simulate an exchange? You should always ask that question before starting any project. And then finally, I'll give you a high-level overview of how you would actually simulate one of these low-latency exchanges. Quick bit before we go any further. IMC. So I work for IMC. We're a global market maker trading in more than 100 markets globally. If you want to know what market making is, I don't have time to discuss that now, but come talk to me after, happy to do so. The core thing for us is algorithmic trading and advanced technology strategies. So please do look at the website or come to me if you want to find out more. Quickly about myself. So I've worked for IMC for the last 6 years. I currently lead our European and Brazilian execution teams. So these are the teams developing low-level C++ execution systems. So please feel free to talk to me about that topic if you're interested in that as well. Without further ado, let's set the landscape. So high-frequency trading landscape. First question, what is an exchange? So it's a marketplace where buyers and sellers can exchange products at agreed prices and volumes. Cool, nice definition. What does that mean in practice? Let's look at what that means for an implementation. So the key thing is that one implementation in automated trading venues uses a so-called central order book. Now, what is a central order book and why do you care? You care about it because if you're going to simulate the exchange, and this is how it's taking orders and matching them against other people, you need to understand how this data structure works to build your simulation. So we'll first dig into how a central order book works. So what I've got up here on screen is a representation of the prices and the amounts that people are willing to buy or sell a product at. So you've all been drinking our coffee, hopefully, over the last 3 days. Imagine right now we're in one of those coffee markets. You want to buy or sell your cups of coffee. Up here on the screen right now, we have a market going on with all of the buyers and sellers here. So you've got volumes, prices, and you've got those for the bids and the asks. Why two? So bid, if you've ever been to an auction, you're bidding for something. It's how much you want to pay for something. The maximum price you want to pay is your bid. The ask side, if you're the seller, it's the amount you're willing to sell at, minimum, no less than that. I'm asking for this price from you in order to part with my product. You have to give me something in return. This is what I want in return. Volume, how much of that thing is available for that price. So IMC's been giving out free coffee, so you've had infinite on the volume right now for the last 3 days. But in the real marketplace, you wouldn't have that. You'd have a set amount of supply and demand here, and the volume represents that. So this is a central order book representation at one point in time in the market. This is a dynamic structure that will update as we go through across the day. So one thing you need to know about central order books, and this is why HFT is called high-frequency trading, this price-time priority feature. What we mean here is that the best price and the first order at that price win. It's the king. So for the bids, what that means is the person with the highest bid wins. I'm willing to pay the most for this product, I should win. For the seller, it's the person with the lowest price. I'm asking for the least from you, so I should win. If we both are willing to trade at the same price, if I get there first, it should be mine. And that's why high-frequency trading is such a low-latency game, because we need to be able to compete in this price-time priority marketplace. So that's a central order book. Let me now walk you through an interaction with that, because if you're going to simulate something, you should understand the dynamics of how it operates. So I'm going to have an aggressing sell request. Let's unpack what that means. So we call it aggressing because it's coming into the marketplace. It's going to take some volume or some liquidity or some product from that market. So it's an aggressing order. Somebody wants to sell. So they've got some product. They want to give it to somebody else. And it's a request because it may not be permitted by the exchange for some reason. So request comes into the central order book. What the exchange is going to do is look at the central order book for the coffee products and say, OK, can anybody match against this order? Can anybody trade against it? Now, the key thing to note here on this order is it's willing to sell for a price of 10 GBP and 150 lots. Because I'm looking to sell, I'm looking across at the bid side. So bid volume 100, bid price 10. This order request will match against that resting order on the bid side. So there'll be a trade going at 10 GBP, but there's not 150 lots. There's only 100 lots. So we'll trade out against that bid, but there'll be some left over. So let's do the trade. So summary here, 100 lots have traded against that resting bid on price 10. And we've got a trade coming out for 10 GBP of those 100 lots. There's still 50 left. How are we going to handle this? Details, but suffice to say, if it was a day order that rested in the book, you would place the remaining amount of that volume on the ask side, because they still want to do the rest of that order at the price they're asking for with the volume of 50. We obviously have to reshuffle the bids, keeping our price time priority going, and this is now the new central order book after a trade. What you've got here is the basis of all of the high-frequency trading world just slowed down. So imagine this going at millions and millions and millions of times across the day, and you get a sense of the speed that we need to operate at here for this. So let's take a look at what generates these order requests. It's a trading system, but you're probably going to ask me next, what is a trading system? What's the magic behind the scenes? So let's slowly start peeling back a layer or two there. So I'm going to give you my very high-level definition of a trading system. It's something that can run one or more trading strategies, and it provides those strategies with the ability to execute requests whilst doing that within risk limits. We don't want to have a strategy that goes haywire and loses a lot of money or causes issues in the marketplace. HFT system does it very, very quickly and can handle many, many requests and responses in a short period of time. So keep that definition in mind. Let's move forward. What is a trading strategy? This is basically just saying it's an algorithm. Nothing more than that. We take some inputs, in this case is an exchange feed, we do some computation, and we produce some output. These could be requests to send to the exchange, it could be positions you want to get into, and you would do all of this within some risk limits that you want to have the strategy work within. So now you know about the central order book, which is the exchange, and you know about a trading strategy, which is what we connect to the exchange and we try to make money with, hopefully. So how do these two systems interact? Let's take a very high-level 10,000-foot view diagram of this. This is it. Nothing more to understand. So you've got two boxes, the exchange and the trading system. The exchange is obviously owned by the exchange. The trading system is us, market participants. And then between the two, there's some communication. The exchange is publishing feed. If you saw Jody's talk earlier, he's given you a definition of this already, but basically it's any updates to that central order book. What traded, what got added to the book, removed from the book, modified, etc. And then we've got orders. This is bidirectional. It's going between us, the trading system, and the exchange. These are the requests. I want to put this order in at this price, and then the exchange saying, hey, your order's accepted, or no, your order's rejected. And we do this back and forth, back and forth. To simulate it, we need to understand it. So let's peel back that blocks that is the exchange. I'm going to focus on three main components here that we'll need to simulate. First is the matching engine. So this is the component that maintains that central order book. It receives those order requests, as we saw in the example earlier, puts them into the central order book, and provides any updates to those participants based on those requests. The order gateway is the gateway to the matching engine. It is the component which we connect to in order to get access to that matching engine. It's responsible for ensuring that we are good market participants, we're using the right sessions and all these sorts of things. And then you've got a feed publisher, which takes output from that matching engine and is responsible for distributing it to all of the market participants. Those are words. Let's try and show how this all fits together to give you a picture in your mind. So here I've got a data flow diagram. And this is, again, simplified, but bear with me on this one. I'm going to start from the bottom. So you've got your trading system. That's something that we at IMC or other companies would build. You may or may not have an FPGA. This is a field programmable gate array. It's a piece of hardware you can program in a language like System Verilog. They're very, very fast, very powerful, very exciting. And you would have one of these and/or a trading system connected into a switch. So in order to simulate the exchange, we need to understand the networking infrastructure, the latency characteristics of that networking infrastructure, because we need to do things like delay modeling, etc. We'll get onto that later, but just bear in mind, we have to get to this level to build an accurate simulation. Now, our order requests and messages to the exchange will hit that switch. That sits on our side, the trading participant's side. In a colo location, we are physically in the data center with the exchange. They give us a patch panel. We are allowed to plug cabling into that patch panel and do anything we want on our side of that, but we can't touch anything after that. So this switch would be on our side, we'd plug into their patch panel, and then from there it's the exchange's network. Now, the exchange may have a series of switches, depends on their architecture and their redundancy setup. Again, we need to understand how their network works in order to accurately simulate it in our models. Those switches will eventually reach hosts that are running the order gateway and the feed publishing systems. The order gateway will lose the exchange order protocol, normally over TCP. The feed publisher will publish UDP datagram packets towards us, and those two systems will connect directly to the matching engine. Now again, high-level diagram here, but if you understand that you need this level of networking knowledge in order to build accurate simulations, then we're good for this talk. Now I keep talking about we need latency distributions, we need numbers. To help you picture this, I'm going to give you some rules of thumb. So I'm going to give a very loose definition of reaction time. It's the time from a trigger, in this case maybe a feed packet, is received to the time we put an order out. Now, I'm giving relative orders of magnitude here for different technologies, so take these with a touch of salt. But basically, we used to say Java reaction time is around milliseconds. Yes, it can be faster with modern techniques. C++ would say about 10 microseconds. FPGA, 100 nanos. Time to cross a switch, 100 nanoseconds, can be faster, depends on which switches you're buying. And then the time taken for light to travel down 20 centimeters of fiber, it's about 1 nanosecond. Now, if you can imagine you've got these switches in large data centers, there can be quite a bit of cabling. If you've got switches that take 100 nanoseconds to cross, that cabling adds up. You need to know about it to build accurate simulations. So keep these numbers in mind, relate them back to that diagram, and just have to think of all those different connections and how they link together and how you're going to have to account for all of that information when you're building your delay models. So with that, we've now got the landscape. That's what we have to think about when we're building these systems. I now need to answer the why. Why would you do this? We have two goals. First goal, we want to develop profitable trading strategies that won't take us down, i.e. they operate within risk tolerances that we're happy to trade within. And it's not just enough to develop a strategy. I need to know whether that strategy is going to behave as I intend it to behave in production. And the only way to check something without putting it in production is to run it with a simulation. So this is why we simulate strategies before placing them into the market. To make that more concrete, simulating means that we can actually backtest our strategies on historic data. It means we can then select optimal configurations and tune our parameters. So yes, if you're thinking machine learning models here, you're exactly right. These are the sorts of things you would use in these trading strategies. You could also not use machine learning models. You could do human-based heuristics. And the second part is that we can match the actual production behavior against the simulated behavior, which means I can explain to a regulator why my strategy did what it did, because I have this explainability characteristic to it. So with the why answered, let's dig in now and talk about how we would simulate at a high level. So I've got non-production level requirements here. So I'm ignoring scalability, performance, etc. These are functional requirements I would need the system to be able to handle. So I need to be able to replay production feed that we have captured. If I'm going to simulate the central order book, I need to know what orders are in the central order book at the time my trading strategy is operating. So I need to be able to replay that information. I need to be able to run my trading strategy against the matching engine, and I need the simulation to be able to handle those requests and get them to the matching engine. I need to simulate the central order book itself using that feed and my order requests. I need to model any exchange dynamics that occur when I'm interacting with a central order book. So let's say in the feed, you don't have a trade from your strategy. Now I trade with my strategy. I need to update the feed and all these other things that are coming through in order to reflect accurately the behavior that we've caused in the market. And I need to be able to get responses and notifications back to my trading strategy so we can continue to trade against the central order book over time. What I want to do now is show how that looks like in a data flow diagram. So let's start at the bottom with this, the strategy part. So I said earlier in my definition of a strategy, very simplistic definition, it takes some feed and produces some order requests based on that feed, as well as any other inputs you may want for simulation purposes. So strategy gets feed in, it pushes out order requests. I have an order API at this point. Why do I have that? I need abstraction. This trading strategy shouldn't care whether it's connected to a simulation or whether it's connected to the real exchange. It should be agnostic of that. This order API provides that abstraction layer to make a boundary for us. That order API is responsible for pushing the order requests into the event queue. And that event queue is making sure that the order requests or responses when they come back are dequeued at the correct points and fed back into the order API to get to the strategy. The event queue is also responsible for dequeuing feed events. Where does it get those feed events from? There'll be a feed producer. Where does that get its data from? Packet captures. All of this is then being fed into the matching engine simulation as well. Again, the event queue is determining the right time based on delay models when to do this dequeue and to feed it through. So the matching engine is therefore receiving order requests, and it's receiving feed. It's then feeding back into that event queue the responses based on its simulation of the central order book dynamics for the trading strategy to be able to pick up and then handle. So this is the high-level data flow and how everything fits together in the simulations. You can obviously break these parts down, add more parts, but this is the core part of the network. Now, I have some questions to consider. Unfortunately, I don't have time to get into these now for you, but I want you to start thinking about them, and maybe you can have a chat with me afterwards, and we can see if you've got some cool ideas here. So how do we account for market impact? That's the impact our requests have on the market, given that we're using production feed, which doesn't contain our orders in the simulation. This is an interesting topic to think about. Data input. How do we get the production feed? So I've mentioned feeds coming over the network, but in a data center, we may have hundreds of cabinets. There'll be hundreds, if not thousands, of feed lines, and all of those feed lines will be feeding data in at different rates, potentially with differences between them. Your trading strategies will run on many different boxes, potentially. How on earth do you match up all that dynamic data against your trading strategy to be able to simulate it accurately? And then when you're trying to do production matching, you've got a lot of differences there you have to account for. So how do you build a system that can handle all of that complexity? Again, no answers forthcoming now, but stuff to think about. So another port here is packet captures. As Jody mentioned in his previous talk, these are exchange-specific. Exchanges have specific protocols for this. Do you want your strategies to know those details? Sometimes you do, sometimes you don't. How do you build interfaces that can abstract over those details or expose them if you need them? Should the matching engine therefore be exchange-specific or generic? Again, sometimes you need details that are specific to an exchange, sometimes you don't. How would you build the implementation to do that? And how would we sequence events? So I've mentioned time being one thing here. But as I've also mentioned, you've got many different inputs. They can all have very fuzzy timing constraints. So how are you sure of the event sequence? And also, if you're working on some exchanges, they won't give you very accurate timestamps. They may give you only millisecond timestamps, which are maybe accurate to maybe a second, and they may have insufficient accuracy in order to build a good simulation. So when you have that difficulty, how would you provide sequencing in those sorts of environments where you don't have maybe accurate timestamping information? Again, no answers at the moment, but think about the problem. And then delay models. So when should these order requests actually land in the book? I showed you the networking setup previously. I showed you all the hosts. Those have all got variances, latencies, characteristics. How do you model that? How do you drive data for that? And then finally, what responses should be received by the trading strategies and when should they be received? Again, that depends on these delay models. But you also have to account for the delay that your trading strategy itself will have, because that obviously has a compute wire-to-wire time. So you need to be accounting for the compute time of your strategy itself. So with all of those questions in mind, let's start by just saying for a simulation what you would require. So I need a realistic simulation, and that's in order to be able to get good match rates between what I'm seeing in production against what I'm seeing in simulation. If I don't have a realistic simulation, my P&L graph could be like this, and then in production, like this. And we want to avoid that one at all costs, so we need realistic matches between the two things. So what do we need from that diagram, taking it forward? I need feed data. I need an order request and response model. I need a simulation loop, an event queue, some delay models, a matching engine, and some strategies to emulate. So let's start walking through those parts. Feed data. So what I've got here is a high-level example of some feed data. I've kept it fairly trim, but you've got some order add requests. So the security ID would be like the coffee product. The exchange order ID is an identifier that we can provide to the exchange, or the exchange can provide to us in order to identify this order. A price, how much we want to pay. Volume, how much the volume is, and the side on it. We've also got order modify, order delete, and the trades, which we saw previously in the central order book. Now, in the feed, you can get any one of these events. I've just got 4 in this example. There could be many depending on the exchange. But at a high level, this information is what the exchange has made public to us over UDP or another protocol, and it's what we need to receive and therefore model in our simulation here. After feed data, we need to be able to get our requests into the matching engine via the order gateway. So at this point, we could have a very simplistic data model for this, but again, you have an add order. This is the security in which you want to add the order, price, volume, side, a client order ID to allow us to track it. I can modify that order, that is, I can change the price or volume of it, and I can also delete that order, again, using my client ID for tracking here. Now, for the responses, I can be told, yes, my order's accepted, ACK, no, my order's rejected, reject, and I can have the same thing for modify and delete. And again, this is just a small part of the overall model you would need to build to model the full dynamics of any exchange protocol at a generic level, but this hopefully gives you a sense of what you would need to do at the basic point. So delay models. Now, we've mentioned you need to calculate the landing times for order requests, and we've also mentioned on the feed side, you need to do some delay modeling. What we need to know here is how long it takes the exchange to publish an update to their feed from when it's matched in the matching engine, how long it takes to go across the network, and then how long it takes our feeding application on our trading strategy to pull that feed into our trading strategy. My answer for how to derive these is modeling and production analysis, and if you want to find out more, come talk to us afterwards. Simulation loop. So this is, as you would build in any simulator, a loop that just goes over a series of events. So I have an event queue, I have a feed reader pulling my feed events, and then from my start time to my end time of my simulation, I will run through. I will grab events from my feed, I will grab events from my trading strategy, I will grab events from anything producing an event. I will work out using my delay models when I should dequeue those events, and then I will add those events into my queue, and I'll make sure that I have a handler that gets called when the event is eventually dequeued to trigger the next stage of the simulation through. And then we just advance. So this is effectively, if you took a really complicated simulation down to its core, all that's happening behind the scenes. We're just running through this loop. The event queue. So obviously, we've got a few things going on here. I mentioned we've got feed, and I mentioned we've also got the order, add, delete, modify requests coming in from the trading strategies. The event queue is responsible for providing a single global truth across the whole system of when these events occurred and when the system should handle them. So that means a simulation event needs to be able to contain all of these different types of events. And with this model, you've then got a system that's able to run your trading strategy. So how would you do the event queue? Again, in any simulator, you would have an event queue. It would be a similar implementation. But effectively, you need to be able to in-queue an event, have a time at which you dequeue it, have a handler for it, and you need to be able to advance the simulation through pulling events off and handling them as the simulation advances. I've got a priority queue here, for example, because in order to provide that global source of ordering, you need to have something that tells you what the ordering is. So here, for example, I've got an event comparator, and I want a min heap because I want the event that's going to have the lowest timestamp to be the first one I pop from the queue. You would add more functionality to this, but again, this would be the core part of any simulation algorithm you're running here for us. So the matching engine part, this is where it can get quite fun because you have to build this part yourself, and then you get to read the exchange specs, etc., and work out how they're doing it based on the feed and the order responses you see from the exchange. You'll probably talk to your local performance team. They'll have done lots of data analysis, and they'll be able to tell you a lot about how the exchange works, and that can be a lot of fun to have those conversations with people. So matching engine, I've just got a high-level interface here, but we would have some templated type potentially for the price level type and the volume type, as well as the participant that is matching in the engine with us. We have the ability to add orders, modify orders, delete orders. We also have the ability to add in feed events. And so this matching engine obviously has to do more than a normal exchange matching engine, which would just have the top three. Our matching engine has to be able to take production feed, take our order requests in, determine how the feed is interacted with those orders, and then produce sensible responses that will not cause crashes or any behavior that's unintended over time. In terms of how you would implement this, so you could split the bids and the asks into two separate data structures and then have your logic split that way. I don't have time, unfortunately, to get into how to build a matching engine. That by itself is a really cool talk all on its own. You could probably spend hours on it. But just remember, high level, you have this system, it's got this interface, and events are flowing into it. Now, for the trading strategy, how do we build those? How do we build the magic? I'm afraid you have to apply to find out for that one. So if you're happy, come and talk to me afterwards on this one. Definitely happy to explain a bit more on that. But at a general point, we might use machine learning models, we might use human-derived heuristics, and this is where we hire many, many researchers and traders for in order to build these profitable parts of the system. But with this, you have the underlying framework which we can run those trading strategies in, and this is how we build our modern trading strategies. So I've now used my 25 minutes, so I'm out of time. Thank you very much for your attention. I hope you have enjoyed the talk. IMC is hiring, so feel free to come and speak to myself or Martijn after the event if you're interested. If not, please contact us on this survey, put your email address in there and details, we'll reach out, or you can reach out directly to our recruitment representative, Jan, who I'll leave the email up on the board. Thank you for your attention.